Welcome back. Today we are exploring test time scaling techniques for improving model performance by using more computation during inference.
This is an emerging area that could fundamentally change how we think about model capabilities. Traditionally, scaling has focused on training time, bigger models, more data, more compute during training. Test time scaling flips this by asking, can we scale performance at inference time without retraining?
Let's start with the simplest form, sampling multiple responses.
Instead of generating one response, you generate many, say 10 or 100, and select the best.
But how do you know which is best?
For tasks with verifiable answers like math problems or code, you can check correctness.
Generate multiple solutions, test them, and return the one that passes.
For open ended tasks, you might use a separate verifier model to score responses.
Or you could use majority voting. If multiple samples agree, that's likely correct.
This is the idea behind self consistency, which we mentioned in episode 16.
Sample multiple chain of thought reasoning paths and take the most common final answer.
Research shows this can significantly improve accuracy on reasoning tasks.
The trade off is computational cost. Generating 100 responses takes 100 times the inference cost.
But you're translating compute into higher quality outputs without any retraining.
Let's talk about verifier models more deeply.
A verifier is a model trained to judge the correctness or quality of solutions.
For math problems, you might train a verifier on correct and incorrect solutions.
The verifier learns to predict whether a solution is likely correct.
Then at test time, generate multiple solutions and use the verifier to rank them.
This is related to process based reward models used in RLHF.
The verifier can provide supervision at inference time rather than just during training.
Another test time technique is iterative refinement.
Generate an initial response, then prompt the model to critique and improve it.
You might do multiple rounds of this self refinement.
Each iteration uses more compute but potentially improves quality.
The model acts as both generator and critic.
Research shows this works particularly well for tasks like essay writing or code generation, where iterative improvement is natural.
Let's discuss beam search and its relationship to test time scaling.
Beam search maintains multiple candidate sequences during generation, expanding the most promising ones.
This explores a broader space of possible outputs than greedy sampling.
Wider beams mean more computation but potentially better results.
However, for language generation, beam search often produces repetitive or generic outputs.
Sampling based methods with verification tend to work better for open ended generation.
But for structured outputs like translation, beam search can still be effective.
Now let's talk about speculative decoding, an interesting efficiency technique.
Speculative decoding uses a small draft model to quickly generate candidate tokens.
Then the target model verifies them in parallel.
If the drafts are correct, you've generated multiple tokens in one pass of the target model.
This speeds up inference without changing output quality. It's exact, not approximate.
The speedup comes from hardware parallelism and the efficiency of the draft model.
There are also methods like Medusa and look ahead decoding that generate multiple tokens per step.
Medusa adds extra prediction heads that predict several future tokens simultaneously.
These are verified by the main model and correct ones are accepted.
Look ahead decoding similarly predicts multiple tokens ahead and verifies in parallel.
These techniques effectively use more test time computation to reduce latency rather than improve quality.
But they demonstrate the broader principle of test time compute trade offs.
Let's discuss process supervision versus outcome supervision.
Outcome supervision only checks if the final answer is correct.
Process supervision checks each step of the reasoning process.
For test time scaling, process supervision can guide generation by verifying intermediate steps.
If a reasoning step is flagged as likely wrong, you can backtrack and try a different path.
This is more sophisticated than just generating complete solutions and checking them.
Research on process supervised reward models shows promise for improving reasoning.
Now, what about best of n sampling?
This is a simple but effective test time scaling method.
Generate n responses, score them with a reward model or verifier, and return the highest scoring one.
As n increases, the expected quality of the best response improves.
This was used in training with RLHF, but it also works at test time.
The relationship between n and performance improvement follows predictable scaling laws.
Another idea is adaptive computation, using more compute for harder problems.
Simple questions might only need one sample, while difficult problems get 100 samples.
The model or a meta controller decides how much compute to allocate.
This optimizes the performance efficiency trade off.
Let's talk about tree of thoughts and graph of thoughts.
These are structured test time search methods.
Tree of thoughts explores multiple reasoning branches in a tree structure.
At each node, you generate several possible next thoughts.
You evaluate these thoughts and expand the most promising ones.
This is more systematic than simple sampling. It explores the space of reasoning paths.
Graph of thoughts extends this with arbitrary connections between thoughts, not just tree structure.
These methods can solve complex problems by systematic exploration at test time.
The cost is significant computation, but for hard problems, it can be worth it.
Let's discuss the relationship between test time scaling and model size.
Smaller models might benefit more from test time scaling than larger ones.
If a small model generates diverse responses, verification can select good ones.
This could narrow the gap between small and large models for some tasks.
There's research on whether it's better to use a huge model with minimal test time compute or a smaller model with extensive test time compute.
The answer depends on the task, latency requirements, and cost constraints.
For latency sensitive applications, a larger model with single pass inference might be better.
For batch processing, where quality matters more than speed, test time scaling can be powerful.
What about test time training or adaptation?
This is an extreme form of test time scaling where you actually update model parameters on the test input.
You might do a few gradient steps to adapt to the specific input.
This is computationally expensive but can improve performance on challenging inputs.
It's related to few shot learning but with parameter updates rather than just in context learning.
Let's talk about the future of test time scaling.
As compute becomes cheaper and parallelization improves, test time scaling could become standard.
We might routinely generate dozens of responses and verify them.
Better verifier models will make selection more accurate.
And better routing strategies will allocate compute efficiently based on task difficulty.
There's also interest in learned test time strategies.
Instead of handcrafted methods, learn how to use test time compute optimally.
Meta learning approaches could train models that know when to sample more, when to refine, when to search.
Another direction is interactive test time scaling.
The model might ask clarifying questions or request human feedback during generation.
This uses human compute as well as machine compute to improve quality.
Finally, test time scaling has implications for alignment.
If models can improve their outputs through verification and refinement, they might naturally produce safer and more aligned responses.
The ability to check and correct mistakes at inference time is a powerful capability.
So, to recap, test time scaling uses additional inference computation to improve outputs. Techniques include sampling, multiple responses with verification, self refinement, beam search, tree of thoughts, and adaptive computation.
Best of n sampling and self consistency are simple but effective.
Trade offs exist between model size and test time compute, and this area is rapidly evolving as an alternative to simply scaling training.
Next episode, we are revisiting scaling laws with a focus on data, compute, and architectural efficiency.
Thanks for listening.
Until next time, keep learning and stay curious about AI.